The stuff I'm talking about today is joint work with my doctoral advisor, Alexis Vasseur at UT. This is sort of the main project I've been working on for the last year or so. And this paper published, like, I think like January. And it's sort of, it's fairly emblematic of a lot of the work that was in my doctoral thesis. Okay. SQG stands for Surface Quasi-Geostrophic Equation. And basically, everything that I'm going to talk about today is various models for approximating Navier-Stokes equations in a rotating reference frame. Like, for example, atmospheric currents, because the Earth is rotating, and so you have Coriolis force. First of all, let's talk about the geostrophic wind. Geostrophic wind is the steady state solution to this system. It's pretty straightforward. It's entirely determined by the pressure, which is steady, and the fluid will just flow along the isobars, lines of constant pressure, and the speed of the flow is totally determined by whatever speed causes the geostrophic force and the pressure force to perfectly cancel out. So it's steady state, it's really easy to compute, it's very simple. And geostrophic wind is the driving force behind a lot of the large-scale effects in both the atmosphere and ocean currents on Earth.
Are these like the trade winds, for example, the west wind zone, trade wind zone?
That's actually even larger scale. So this would be like when you get the morning weather report and they draw these like circles with arrows on them, those are the isobars, and those are basically determining the flow. And then you have like these really large scale and like long time span stuff, which is also going to be geostrophic, but with sort of a simplified model of pressure. Right, and so if you quasi-geostrophic is a perturbation. You take the geostrophic wind, which is a pretty good solution, and you add an epsilon perturbation. You take the limit as epsilon goes to 0, and you end up with an equation called the quasi-geostrophic equation, which is a perturbation of geostrophic. And that is really practically useful. This is what meteorologists will use when they're trying to get the morning weather report. So it's a very relevant mathematical model. It takes place on a half plane, so you have the horizontal xy plane, which would be the surface of the Earth or the bottom of the ocean, and then it goes in the z direction sort of up indefinitely, and you have the current in this half space. And you also make some approximations about sort of, you assume constant latitude, not too close to the equator, not too close to the poles. And this models both atmospheric currents over land and over water, and ocean currents in large bodies of water. The surface quasi-geostrophic equation basically is an approximation where you assume that the solution is harmonic in the interior. Because of the way the quasi-geostrophic equation works, if your initial data is nearly harmonic, then the solution remains nearly harmonic for all time. And of course, if you just assume that it is harmonic, well, a harmonic equation in a half space is totally determined by the boundary, what happens in the boundary. So this allows you to take a 3D equation and approximate it by a 2D equation. That's the SQG, the surface quasi-geostrophic equation. It was first introduced to the mathematical community by Constantin back in 1993. And in addition to being a sort of physically meaningful thing that was studied by meteorologists even before mathematicians realized it existed, this equation also has an interesting relationship to the Navier-Stokes equation. So I have it written at the bottom of the screen here. You have a time derivative, you have a transport, it's an active transport where the velocity is the Riesz transform of your solution theta rotated 90 degrees, and then you have a dissipation term with variable force nu and variable degree s.
So is everything vector valued at this point or not?
So theta is a scalar, and the gradient of theta rotated 90 degrees is the actual flow. Or
So, but when you say harmonic, I
not
mean,
be exactly right.
I mean, so just trying to get their model right. So you said you have a domain in R2 essentially, and then you have this three-dimensional column of air above it.
Yeah.
And
So
up there, everything is harmonic, but it's still vector valued, right? So
what is? So this is
where's the fluid? That's what I'm asking.
okay. I cannot remember the name of this. It's a name for a variable that defines fluid flow where the actual flow is the gradient rotated 90 degrees.
That's in 2 dimensions. I can't. I mean, you're now in 3 dimensions.
So in 3 dimensions, you would do that only. So the meaning of theta in the horizontal and vertical directions are different.
Okay.
What you would do is you take the gradient only in the horizontal directions and rotate 90 degrees only in the horizontal directions, and that gets you the flow. You actually, one of the assumptions that you use to derive the quasi-Giussic equation is stratified flow, right, where everything, you can't go up or down too much, because then you'd have sort of hot air below cold air, which you won't usually get. And if that stratification assumption breaks down, the equation becomes invalid. So you don't have any flow in the horizontal direction.
So you should think about the theta as some sort of potential that generates the flow upon taking the right kind of derivatives.
Yes, but only in the horizontal direction.
Oh,
in the vertical direction, there is no flow because everything's stratified.
Ah, I see.
And there's the stratification isn't actually horizontal; it's like actually curved, and you do like a change of coordinates to make it flat, which I'm not getting into.
Thank you.
So this equation, you should notice, is pretty similar to Navier-Stokes in vorticity form. So this Riesz transform would be basically the Biot-Savart law, except it's not. The exponent's a little different. In the Biot-Savart, you have a -1 instead of a -1/2. And the advantage of this is you actually get vortex stretching-like behavior even in the 2-dimensional case. So SQG is a good 2-dimensional model of 3D Euler. And that's been sort of formalized in various ways, and this is a sort of an active and fruitful area of research, sort of using what we can say about SQG to say things about 3D Euler. And so in the critical case where S is equal to 1/2, so notice that the first term you have 1 time derivative. The Riesz transform is 0 derivative, so this second term is just 1 space derivative. And the third term has 2s space derivatives. So if you take s equals 1/2, every single term has the same number of derivatives. That's the critical case and the one I'm going to talk about today. And this was proven to be well posed back in 2010 or so, first by Kieslев, Narzarov, and Volberg, independently by Caffarelli and Vasseur, and then later with a different method by Constantin and Vicol. So well posedness has been known for this for 10 years or so. That's all SQG on R2 or the torus. On bounded domains, it's a little different. So first of all, because this equation involves non-local operators twice, both in the Riesz transform and in the non-local diffusion, the boundary conditions are really going to matter, and different boundary conditions get you totally different models. So the first model that was studied was by Denis Krivensov, who was a student of Louis Caffarelli. He graduated, I think, about 2 years after I got to UT. And he, in his thesis, looked at quasi-geostrophic on not bounded regions, but he took R2 and divided it into 2 regions with the boundary. And one was sort of, it's the atmosphere where you're either over air or over land, and over water or over land. And the air over water, the model that he was that you end up with there is a close analog of the model that I was looking at. And so you have to sort of solve it in the interior, and the boundary condition is that you assume you know what's going on over land, and you put that in as the global boundary condition. So that was in 2015. More recently.
Sorry, Logan, I couldn't understand. So in the model over water, there is a free boundary or something like that, and that's.
It's not free. The boundary is the beach. It's fixed.
Okay.
But yeah, so in the open set that is over air, you have a certain type of diffusion, and you have a different type of diffusion over land. And so the over water ends up with just like the critical diffusion. And so if you solve the over land part, that gives you a boundary condition, not just at the beach, but at everywhere that isn't over water. And so you could just use the normal Laplacian where you fix all the values outside of the region in question.
Okay,
so
okay.
The value of S you're discussing right now, right? Are you saying?
No, so,
S? In your previous model, there was a value of S in your class.
So over water, you get S equals 1/2, which is the critical case. Over land, you get a different, slightly different thing. Novak, so when people like use this equation, it's usually like on the Earth, so a pretty large region. When you are doing experiments, you can't really do it at the scale of the Earth. That's difficult to do in a lab. So people do this thing with they take a cylinder and they rotate it at a constant speed. And so that model is the one that Novak and Vasseur looked at recently. And they basically, in the scenario, they rederived the quasi-geostrophic equation, starting with Navier-Stokes, with the Coriolis force, and they worked out what the correct model is, and they were able to show existence and some regularity results. The boundary conditions that they derive are, fairly rigorous in terms of starting from the physics, but they're very complicated. And if you try to look at an SQG, where you assume it's harmonic in the interior, the boundary conditions are really complex, and the fractional Laplacian analog that you arrive at is difficult to study with the methods that are known. There's the thing that's sort of being looked into, but it's a bit of a moonshot. There's a big model that was sort of pre-existing from 2016, proposed by Constantin and Ignatova, that basically is the same as the Novak-Vasseur model, but SQG instead of QG, and the boundary conditions are simplified in the sort of most obvious way. Instead of assuming that you have a function that depends only on height, you take a function that is just constant, which gets rid of all the complications of the Vasseur model, but keeps the conceptual sort of frame of it. And you end up with this really nice model that's been studied by Constantin and Nguyen in it's like half a dozen papers, probably a little bit more at this point. And it uses the spectrally defined fractional Laplacian. And they're able to obtain existence, some regularity results, including smooth solutions in the interior. They look at both viscous and inviscid models and some compatibility results. There's a reasonable body of literature here. Different types of solutions, all of that. So what is the Constantin model? Omega is a smooth, bounded open set, arbitrary. You take the Dirichlet Laplacian on omega, that's Laplacian sub d, and then you take the square root in the spectral sense. So that means you expand, right? You get a countable sequence of eigenvalues and eigenspaces, and you expanded these, and you just take the square root of the eigenvalues. And you end up with this very simple model. And note that the solutions are invariant under sort of any scaling in time and space. So this is the critical equation. Now, obviously in the interior, this model will look pretty similar to the global equation on R2 and on the torus. But as you get closer to the boundary, things become more exotic. And this sort of, one way to see this is that the Laplacian and the gradient commute, but the Dirichlet Laplacian does not commute with the gradient. This is because the Dirichlet Laplacian, it's not translation invariant. If you have a Dirichlet boundary condition on its function and you translate the function slightly, it no longer vanishes at the boundary. And in the interior, you can sort of fudge it and say like, oh, well, let it be like almost the same, but change it. But as you get closer to the boundary, this becomes more and more of a problem. And that means that if you have the commutator of the gradient of the Laplacian, all of our estimates on it blow up at the boundary. There are no estimates that there are very few estimates that are global. And this is really important because the Riesz transform is the gradient and the inverse of the Laplacian. So the commutator of the gradient of the Laplacian is going to come up a lot. And we can't really bound it. And you can say something stronger than this. There's Caccioppoli and Stinga in 2016 derived this representation of the fractional Laplacian, the fractional Dirichlet Laplacian, as a singular integral operator. So this is the standard form for a singular integral operator with a kernel, and they were able to sort of derive the kernel and write it out in some explicit form and compare it to the kernel for just the regular fractional Laplacian in R2. And what you get is that in the interior, these are comparable. There's sort of bounded above and below by up to a constant. But as you get to the boundary, the kernel vanishes and the singular integral operator disappears. Meanwhile, you have this error term that's sort of lower order in character with this kernel B, and B blows up at the boundary in a non-integrable fashion. So in the interior, you can just say it's a singular integral operator just like the regular Laplacian with a small error term. And at the boundary, it is an unbounded operator with a singular integral operator error term. So it really changes behavior.
What's U star and phi star?
That's so that notation comes from Boltzmann. It's a dummy variable. So that's U evaluated at the dummy variable. So you see X and X star?
Yeah, that's right. It's the same function, but the variable differs. Yeah. Okay.
Exactly. Yeah.
Yes.
Right, and this is every singular integral operator is going to look roughly like this if you compute the energy. The only difference is what is K. Okay, so we know the boundaries where the difficulty lies, and this is why sort of prior to this year, you have smooth solutions in the interior, but basically no regularity results actually at the boundary. And so this is sort of my and Alexi's contribution. We were able to show that given any L2 initial data, there exists a global in time solution, which is Holder continuous in all of omega up to and including the boundary. This is a regularization result. So like the heat equation, you start off with like a Dirac and it smooths out if you wait any amount of time, but sort of the longer you wait, the smoother it gets. It's the same sort of result. It instantly becomes Holder continuous, but how continuous depends on how long you wait. And the proof of this was based on the result of Caccioppoli and Visser from 2010, which was showing a similar result for the SQG on R2 and on the torus. That in turn was based on the DeGiorgi method, which is from Ennio DeGiorgi. He invented it to solve Hilbert's 19th problem, and it's seen a lot of application to elliptic and degenerate elliptic and parabolic equations.
I have a question, Logan. So this, I mean, looks like an existence result, but do you prove that for any weak solution, then that happens?
Okay, so we don't have uniqueness quite yet. Yeah. So there exist weak solutions which were already known, and some of them are smooth in the interior, and some of them are continuous up to the boundary. I am blanking on whether the ones that are continuous up to the boundary must be smooth in the interior. I think that's true, but I'm not 100%. So there's multiple non-unique solutions, and we prove that there exists a solution which you have to construct in a specific way that we know will be continuous up to the boundary.
Okay, then this is a little bit different, because if I remember correctly, in Caccioppoli and Visser's result, they proved that the weak, any weak solution to this equation with initial data.
Leray-Hopf, I believe. Yeah, that it's the same thing. We construct Leray-Hopf solutions, and the Leray-Hopf solutions are, but it's not clear that all weak solutions are Leray-Hopf.
Okay, well, yeah. When I said weak, okay, that's what
exactly. Yes. So, but there exist other weak solutions that have been studied in other papers, which are not Luray, or which are not necessarily Luray-Hopf. We don't know.
Okay, sorry for the mess. What I wanted to know is that. So one thing is that you say that your omega is bounded. It is not necessarily
the definition of Luray-Hopf is also like really fucked up in this. It's not like the classical definition. It's like a suited to this precise problem. What were you saying?
Like the boundedness of the omega is supposed to be smooth too, or you can do that for any bounded.
So you need omega to have C2 boundary. Sorry, I can't remember if it's C2 alpha or C1 alpha. I think it's C2 alpha. Yeah, C2 alpha. This is it's the same amount of regularity that you get in basically all the results in this direction.
Okay, I was a little bit surprised. Okay, that's it. Mm-hmm. Sorry, continue. Yeah. I'm sorry.
Yeah.
Mm-hmm.
Okay, any other, I'll move on to the proof after this. Any other questions on sort of the result and its context? Okay. So how do you show this? So the first thing is to take an idea from the sort of original DeGiorgi method, which is you have a nonlinear equation. Let's think of it as a coupled linear equation. So remember, right, you have this linear equation with a arbitrary velocity u, and then you also say that u is the Riesz transform of theta. So both of these equations are linear. Let's think of them as two separate equations and sort of prove something about theta, use it to prove something about u, and then you go back and forth. So because u is a gradient of something rotated 90 degrees, you know that it's divergence free, just regardless of how much regularity you have. And just knowing that u is divergence free, you can pretty easily show that theta is going to be L infinity. It's sort of a non-local heat equation plus this transport, but the transport, because it's divergence free, it can't really accumulate, so you get L infinity. This is all sort of not trivial, but easy to do with known methods. And so since theta is L infinity, in particular, you know that u is not just divergence free, u is the Riesz transform of an L infinity function. So that's the information about u that you bring into this. And then the hard part is saying, just because u is the Riesz transformity of some L infinity function, it doesn't matter that it's theta, it's some L infinity function, we need to show that theta must be Holder continuous. And the way you do this is with sort of an energy method. You take a localized Caccioppoli inequality and use this to show Holder continuity. So take some point x naught where you want to show that your solution is continuous, and look at some ball around it, and you localize theta to that point and that's ball. So theta plus is just, it's the positive part when you're close enough to x naught, and it's 0 when you're far away, and you interpolate in the middle. And then you do the standard thing where you take the equation, you multiply by theta plus, and you get an energy inequality, a Caccioppoli inequality. And so I've dropped a couple terms that show up that are not super important, but the key is that you end up with the time derivative and the HS norm being bounded by the L2 norm and this one term involving u. Psi here is the function you use to localize. It's a constant, right? You can define it explicitly. So you end up with u times theta plus. And the key here is that because you have these first order quantities involving one derivative, bounded by these 0th order quantities involving no derivatives, that sort of should be a little counterintuitive, right? This is the opposite of Sobolev embedding, and it's a strong enough property that you can get your that you can get a sort of decrease in oscillation. And then because this is true at every scale, because this is totally independent of scale, you can zoom in and do it again, and you get a sort of regularity result that is independent of scale and is true at every point in the domain. And by iterating this, you can easily show that the solution is Holder continuous. So conceptually, the only thing you need to show is that this Caccioppoli inequality holds independent of scale at every point.
Now, Logan, so how do you localize near the boundary?
So basically, okay, so sort of how you do it mechanically is you extend by 0 because your solution is assumed to vanish at the boundary. You extend by 0 and you just analyze that theta plus. Actually analyzing the Caccioppoli inequality gets harder when you're near the boundary. So you can't assume that you're sort of far away, and that makes it harder to analyze, but the actual mechanics is you just extend by 0. And so you might be like theta plus might be like 0 up to like a curve and then do something weird inside. Does that make sense?
Yeah, but then I'm a little bit puzzled because then it looks like, well, like you can do whatever you can do in the space. You can do like like you extend that by 0 and then you can do like the usual thing. I mean, like, yeah. I was expecting something different to happen in the boundary for some reason.
So okay, let me.
Yeah. So, I don't want to disturb.
No, this is my next point is will allow me to answer that question. So the complication here is you have this term. This is I called it the HS norm, but it's this lambda I defined a couple slides up. So you should be concerned that like maybe the lambda I defined doesn't behave like the HS norm. In particular, it needs to be coercive. Does this actually control the derivatives? And coercivity breaks down near the boundary. So showing that it's coercive up to the boundary is the hard part. So this needs to be coercive. It needs to be coercive up to the boundary, and it needs to be coercive independent of scale. If as you zoom in, this gets sort of further and further away from the standard Laplacian, then you can't. Then it breaks down as you zoom in, and it's not a dependent scale.
You must be using something about the domain here.
Only that it has smooth boundary.
Yes.
Mm-hmm.
Right. Yeah, but you do need that. Or C2 alpha.
Yes.
As the case may be. The other problem is this U-term. Remember, the only thing that I know about U is that it is the Riesz transform of some L infinity function. That's not a lot of information. So we want to like bound this. We want to say like, okay, D psi, that doesn't matter. U, that's L infinity or something. And this is bounded by just the L1 norm. And then if you have that and coercivity, you're done. So how do we get those two things? Independent of scale, all the way up to the boundary. Okay, so coercivity. This was known beforehand, so I don't want to imply that it's new, but I think it's conceptually important. We need to show. So take this definition of the fractional Laplacian, which is well studied, and we know it has, in particular, it has a Sobolev embedding. And also, what's the one that gives you compactness with a derivative, with some amount of derivative? I can't remember the name. What is it? Stokols? No.
You mean Kondratiev?
Anyway, Relic-Kondratiev. You have a Sobolev embedding and a Relic-Kondratiev result for this form. And you want to show that it's bounded by the form that you actually control. And this constant C has to be independent of scale. And this is relatively easy to show by interpolation. Sort of when S is equal to 0, both of these will be just the L2 norm. And so you have this inequality with constant 1. And when S is equal to 1, both of these will be the H1 norm, which remember is locally defined just in terms of the gradient. So in particular, both of these definitions of the fractional Laplacian are equivalent when you're just talking about the gradient. So again, at S equals 1, you have this inequality with constant C equals 1.
Why do we have, sorry, S equals 1? Oh, it's a half Laplacian, but you put it on one side, yeah?
So so I'm referring to this.
You're using Dirichlet conditions, you put it on. So the lambda is still a non-local operator, but you have it twice, right? Lambda F, and so you put them all on one side?
Yeah, so this is the integral.
And then it becomes, this is the Dirichlet integral, right?
Yeah, so you get the Laplacian theta times theta, which is equal to the integral of the gradient theta squared. You just integrate by parts. And you can do this in both definitions. You can do this trick.
I see.
So I may be missing something obvious, but when S equals 0, Is there a reason why this has to be the L2 norm? I'm missing something sort of.
So, okay, so I was a little worried about saying that this formula as written down won't equal the L2 norm when s equals 0. It's more that this formula can be seen as an interpolation between the s equals 0 case, which will just give you between the L2 norm and the H1 norm. Both sides of the inequality interpolate between the L2 norm and the H1 norm in different ways.
Okay.
And so because you have equality at the endpoints, you have equality with the same constant for all values of s.
So even the convergence of these integrals is delicate anyway, right? Because you're not locally integral in the kernel.
Yeah.
So I think s equals 0, I think it's just as fine as positive s, but these are very improper integrals, principal value integrals.
This C2s is going to fix a lot of the problems that show up. Yeah, it's... Anyhow, you get this inequality for all s between 0 and 1, and in particular, your constant is 1. The number 1 is well known to be independent of scale. It does not depend on omega. So we have coercivity independent of scale, and this works even up to the boundary. So if you take if you take a solution that sort of pokes out of the boundary a bit and will sort of vanish outside of omega, this argument still applies, and so you still get coercivity, even if you're at the boundary. Okay, so we have coercivity. What remains is to control the quantity u. Okay. What would be nice is to take our sort of the fact u is the Riesz transform of an L infinity function and translate that into u is bounded in some Banach space. And so the question comes up: what Banach space would be appropriate here? What Banach space encodes the information that we have on u? And that Banach space needs 3 properties. First of all, the Riesz transform needs to be bounded from L infinity to whatever space we pick, otherwise we don't actually have control there. We also need the Banach space to be strong enough that this integral of u times theta plus is actually bounded. If we can't control the integral, then what's the point? And it needs to be scaling invariant. So as we zoom in, arbitrarily, u can't grow in this Banach space that we choose. It must start small and remain small no matter how much we zoom in. It would be very nice if we could bound u in L infinity. So this almost works because the Riesz transform is bounded from LP to LP for all p strictly between 0 and infinity. But it doesn't work for L infinity. Notice, of course, that this would be plenty to bound the integral. We could just say integral u theta plus is less than the integral of theta plus, and no more u, no more complications, we're done. And of course, L infinity scales the right way. In the paper of Caccioppoli and Vasseur, this is for SQG on R2 or the torus, they just use BMO because the Riesz transform is bounded L infinity to BMO. BMO, so it's a little bit harder to actually bound the integral using BMO because you have this sort of up to a constant thing. But with John Nuremberg and with a very clever use, a way of getting rid of that constant, I'm not going to get into it at all, but the thing where you have to get rid of the constant is far and away the most confusing and difficult part of proving this result. It's like mathematically trivial, but in terms of actually like doing the calculations and writing it down, it's horrible. But anyhow, if you do that trick and get rid of the constant, you can bound the integral. And of course, BMO scales the same way as L infinity. The problem is there's not like a ready-made result that says that that Riesz transform on a bounded domain is going to be bounded from L infinity to BMO. This is something along those lines is true, but it's not like a prepackaged result. So we sort of had to dig into what are you actually saying when we say something is bounded to BMO, and we end up looking at the related space B0 infinity infinity, which is a Besov space. I'll define it in a second, but it scales like L infinity, so that's nice. Is the Riesz transform bounded from L infinity to B0 infinity infinity? No, but something close enough to that ends up being true. Is if you have something bounded in L infinity, B0 infinity infinity, is this integral U theta plus bounded? Kind of. It's bounded in a very weak sense, and it's sort of hard to take advantage of that, but it can be done. So that's, I'm going to sort of go into a little more detail on how you actually do get this bound, but that's the ball game. We have this localized Caccioppoli inequality. It's coercive. The U term can be controlled. That means that it's sufficient to show this decrease in oscillation. And if you zoom in, because everything is independent of scale, you get decrease in oscillation at every scale, which is equivalent to continuity. So that's sort of the overview of how you prove this. So how do you actually deal with this B0 infinity infinity space? What do I mean by that? So this is, I'm looking at the best out space is defined in terms of Littlewood-Paley operators. Now notice the Littlewood-Paley operators are defined in terms of the Fourier transform, and the Fourier transform doesn't really work on bounded domains as well as it does on say R2. You can sort of, it's equivalent to this spectral decomposition, right? But it's equivalent to, not the same as, and you have to rederive a lot of the ideas, and they all like are analogous but change slightly. So Littlewood-Paley operators, so you have, so you look at a function and you sort of parameterize it by the eigenvalues, lambda 0, lambda 1, lambda 2, etc. And you take sort of, so to take for the Littlewood-Paley operator Pj, you look at where lambda is approximately equal to 2 to the j, say between 2 to the j minus 1 and 2 to the j plus 1. So you get this dyadic interval, and you say, you sort of smoothly cut off. So you're only looking at the frequencies, the lambda sub whatever, that are between 2 to the j minus 1 and 2 to the j plus 1.
So these are spectral projections, basically?
Yes, yes.
That commute with the Laplacian? Yes.
They're not, of course, projections exactly, because you'd have to have sort of an indicator function, and this is a smooth cutoff, but they're pseudo projections. Mm-hmm. And they sum to the identity, and they allow you to sort of isolate different frequencies.
So if this was on the whole space, this would be Fourier multiplication operators?
Yes, they'd be Fourier multipliers by a sort of, like what I've drawn, except on an annulus, okay, instead of just on R+. Now, in the full space R2, you have these things called the Bernstein inequalities. The Bernstein inequalities are very nice. They tell you basically, if you take a projection onto the J frequencies and you take a derivative, that basically multiplies by the quantity you'd expect it to. So this says differentiation is a multiplication operator by frequency. It causes the large frequencies to get very large because this 2 to the sj will be large, and it causes the low frequencies to get very small because this 2 to the sj will be small. And similarly, if you have the gradient mixed with some fractional Laplacian, you get the same result. Derivatives behave as you expect. They make the large frequencies big and the small frequencies small. Now, the downside is that in R2, everything commutes. The gradient, the fractional Laplacian, and the Littlewood-Paley operator, they all commute. That is not true here. So remember, the actual, so if you want to look at infinity 0, so if you want to look at the Besov norm, what this is it's the sup over J of the jth projection, it's L infinity norm. There should be an F in there. So you take the projections of F, you look at their L infinity norm, and you take the sup over all the projections. That would basically correspond to this. You take the theta, you take its Riesz transform, and you take a projection, and you look at the L infinity norm. But this is not covered by the Bernstein inequality. So this is where the lack of commutation really bites you. But to solve this, all you have to do is to put the projection onto the other side. So this now looks, this Riesz transform of the projection instead of the projection of the Riesz transform. So this is not actually the B0 infinity norm, but it's a related quantity that you can analyze by looking at the Bernstein inequalities. I forgot to mention, so all this sort of Littlewood-Paley stuff adapted to bounded domains was sort of, the reference that I was able to find is a recent result by Iwabuchi, Matsuyama, and Taniguchi, who developed this whole calculus, sort of defined the operators and some related concepts, and they derived the Bernstein inequalities. This is really great work. Anytime you want to do Fourier analysis on bounded domains, I can't believe it took till 2017 for someone to write this down. It's very useful. Okay, so we want to look at the Riesz transforms of the different projections of theta and say that these are bounded at infinity independent of J. Okay, so if we can bound these projections, why is this enough to actually get control? You decompose U as the low frequency part, which is the sum of the Riesz transforms of the low frequencies. Note that U itself is not low frequency, because once you take the Riesz transform, who knows what happens to the frequencies? But it's the Riesz transform of something that is low frequency. And because it's a Riesz transform of something that is low frequency, you should expect it to be Lipschitz. Similarly, you take the sum of the high frequency parts, and because it's a sum of the Riesz transforms of high frequency things, you expect it to be so not smooth but integrable, which are equivalently, if you take off a little bit of derivative, it ends up in L infinity.
So if you're in a bounded domain, should that be, I mean, that low part, there shouldn't be much at all, no?
Yeah, yeah. Very good question. Very true. There's some smallest eigenvalue, and for J less than the log of that eigenvalue, these will of course vanish. So this infinite sum is a finite sum.
Yeah.
The problem is the smallest eigenvalue depends on the size of your domain. So as you zoom in, the smallest eigenvalue gets smaller and smaller. So while this is a finite sum, if any of our results depended on the smallest eigenvalue, then that result would not be independent of scale.
No, but the small domain has a large eigenvalue.
No, as you zoom in, the domain gets bigger.
I see.
Yeah, as you zoom in, the domain gets bigger, and so your smallest eigenvalue gets smaller and smaller. So there's some J naught below which all these projections vanish, but you need the result to be independent of J naught. So rather than show that this is, bounded because it's a finite sum, we show that even if it were an infinite sum, it would still be bounded. And that means that even as the sum gets sort of longer and longer, it remains bounded.
So all your bounds are independent of the size of the domain. That's what you're saying.
Yes. And so for that reason, while we can sort of qualitatively use the fact that this J is actually bounded below, we can't use it quantitatively. Okay, so we just need to control these two parts. Remember, the low frequencies are Lipschitz, and the high frequencies are in this W minus epsilon infinity, which means if you remove some epsilon number of derivatives, the result is going to be bounded, which is something you should expect for high frequency things. Because when you move derivatives, they get really, really tiny. And then it's sort of, with these two facts, that is enough to control the integral U theta plus term with some sort of standard tricks. The Lipschitz control is really easy. You want to look at the gradient of the low frequency part. So that's the gradient of the Riesz transform. I'm blanking on the name of this theorem too. But it's a standard one that the L infinity norm of the Laplacian and the L infinity norm of the Hessian are comparable. I can't remember who this is named after, but it's a sort of standard result. It's in Gilbart and Trudinger. So we need to bound the L infinity norm of the Hessian. Bounding the L infinity norm of the Laplacian is really easy because the Laplacian computes with everything. And this is, in fact, these quantities are geometrically decreasing, so in fact they're summable, even if you take j down to negative infinity, and so we have a bound. That one's straightforward. Mm-hmm.
Sorry to interrupt, but so if the Hessian and the Laplacian being comparable on L infinity sounds like very close to saying the Riesz transform is bounded at L infinity. If this is too technical and getting into the weeds, feel free to but it just, that's sort of surprising to me.
Yeah.
Or isn't that just elliptic regularity theory somehow?
Yeah,
that you you know, solve Laplace u equals f, and then you get control over the entire, you know, f and w2.
Yeah. Yeah, that's my thinking. So it doesn't say that because I know that the Riesz transform isn't bounded from L infinity to L infinity. Yeah, I'm not sure. What to say about that?
I just mean because the Hessian will be like the Riesz transform tensor the Riesz transform of minus Laplace, right?
Right?
Never mind. Anyways, so I'm sorry that I'm getting into the weeds.
And then the one on the
I see
right.
What you're saying. Sorry.
Sorry.
Yeah, Evan, I see what you're saying, and I can't off the top of my head see why it's not right, but I'm pretty sure it's not right. Yeah.
No,
you saying?
I'm sure you're correct. I'm just, if there was a simple explanation, I was curious. I don't want to get too much, I don't want to derail this with some complicated harmonic analysis question. So.
Okay.
Right. And then on the last one, the third sum that you're having here, you're just commuting the Laplacian through the lambda inverse. Is that basically what you're doing?
Yeah, so, well, the Laplacian and the lambda inverse is just lambda, and then by the Bernstein inequality, this is like 2 to the j, and 2 to the j is summable from 0 to minus infinity. And again, in fact, this is a finite sum, but it doesn't matter. It's summable all the way to minus infinity. Okay. So then the hard part is controlling the high frequency terms. So if we want to take lambda minus epsilon of the high frequency part, we do the same thing. We sort of commute it through the sum with the triangle inequality, and we end up with lambda minus epsilon of the gradient of lambda inverse of the projection. And here we have these lambdas on either side of the gradient. They want to cancel out, but they can't because they do not commute with the gradient. They can't get to each other. We can't apply the Bernstein inequality. This is difficult to deal with. And notice what's happening here is you start off with this, like, the jth projection of theta. And then when you apply lambda inverse, it remains, so it's localized at the jth frequency. And when you apply lambda inverse, it remains localized at the jth frequency. And then when you take the gradient, we don't really know what happens. And then we want to, lambda minus epsilon is only going to behave well if it's still localized, which it may or may not be, we do not know. So the problem here is the localization frequency might get broken by the gradient. Let me draw a diagram for this. So we have, so let's look at what the gradient does to the localization. We have PJF, which is localized around some jth frequency, right? So this is PJ of F. It's localized. After we take the Laplacian inverse, it remains localized. It just gets multiplied basically by some number. And then we take the gradient. Well, what can we say? So fix mu, which is the sort of the frequency that we're trying to look at, and take some function g, which is an L1, as a test function, and see what bounds we can get. Well, if you do the obvious thing, you get the muth projection of j, and then this Riesz transform of the jth projection of f, and you see that it's bounded by the L infinity norm of f, which is to say, after you take the gradient, none of the frequencies end up bigger than the only frequency that existed beforehand. That's pretty trivial. So the frequencies don't get any bigger than they were before, but they now could be anywhere. But if you just integrate the parts again, and put the gradient on this p mu of g, you find out that actually, if you look at the low frequencies, they decrease exponentially. And then the high frequencies, well, they increase exponentially, but we already know they were bounded by a constant, so you end up with a thing that looks like this. Right, so they start off localized, you take the gradient, and now it's exponentially decreasing to the left and then bounded by a constant to the right. So this tells us that the frequencies get smeared out a little bit, but in a predictable manner when you take the gradient of something that's localized in frequency, which is a commutation relation on the gradient and the Laplacian. It's a subtle commutation relation, but that's what we're saying. And then, so with this fact, it's a very sort of weak result, but it's what you can get, and that is enough to tell us that this expression lambda minus epsilon of the gradient of lambda minus 1 will be summable. In particular, when you take the large parts, that's summable because you have this lambda minus epsilon, so you expect the large frequency parts to be summable. And when you take the small frequencies, less than j, then the fact that you have this exponential decay makes them also summable. And so the result is that this is L infinity, and it's summable in L infinity, and you get the bound you need. Right, so that's a little in the weeds, but the point is, with this little paleocalculus, you end up with a commutation relation that is sort of exactly what you need, and you get that U is a sum of something that's Lipschitz and something that's integrable. And combining these two facts and being clever, you end up with the integral of U times theta plus is well controlled. It's controlled independent of scale because this control you have on U is all L infinity norms, just L infinity norms of different quantities. Yeah, there's a small issue of sort of how the projections change when you zoom in, but you can deal with that. And then with the Georgi argument and the localized Caccioppoli inequality, you get continuity up to and including the boundary. So that's everything about the proof. So things that are sort of still open is, so first of all, we have Holder continuity. So once your solutions are C1, I haven't seen a proof of this, but it's generally believed that you can get C infinity pretty easily after that. But getting from C alpha to C1, so this is the thing I've been thinking about and would like to think about more. But there's sort of, I'm not yet sure whether this is true. And this is sort of an open question that I'm very interested in. I know that, I know Constantin was looking at it for a bit. So this is a cool thing. People should think about this. And then there's also sort of some more basic questions about the model, sort of how physically meaningful is this? Sort of, it's not quite the Novak-Vasseur model, which we have more confidence in its physical meaning, and sort of how far apart are these? And can you apply these methods of analysis to the Novak-Vasseur model or something sort of in between, right? A little bit closer to the Novak-Vasseur model, maybe, and inch towards that. That's what to say. Thank you.